Hello, everyone. Welcome back to AAS Publishing. We're going to continue another installment of the Author Chat Series, and I am delighted to have Erika Holmbeck with us today.
Hi, Frank. Thank you for having me. So for those who don't know me, my name is Erika Holmbeck. I am finishing up my graduate work at the University of Notre Dame in Indiana, and my research is primarily split into two aspects. So half of it is observational, and half of it is some theory work, but together it is 100% nuclear astrophysics with an emphasis on heavy element production by rapid neutron capture nucleosynthesis, also known as the R process. So on the observational side, I search for, study, and analyze very metal poor, chemically simple stars that are enhanced in these heavy elements created by the R process. And on the theory side, I run R process nucleosynthesis calculations in different R process sites to figure out which astrophysical sites may or may not be responsible for producing the heavy elements that we observe in stars.
That's awesome. You're a proverbial double threat there with observations and theory. So.
Yes, thank you. I've tried.
Next, you'll probably in your postdoc, you'll pick up building instruments, and then you'll be the triple threat.
Oh, geez, that is a lot of work, and I reserve that for someone else.
All righty, very cool. Okay, so we are going to get into your 2019 paper here. So I'm going to do a screen share here. Screen share, preview, share, and there we go. You see it?
Yes, I see it.
Awesome. So actinide-rich and actinide-poor R process metal poor stars do not require separate R process progenitors. Erika, take it away.
Yeah, well, I'm really happy to be talking about this paper in particular because, like I said, my research is half observation and half theory. And this was really the paper where those two aspects of my thesis were brought together. So I'm really excited to be talking about this paper.
Cool.
And this paper follows up on a previous work that we also published in 2019. And basically what we studied in that previous paper was actinide production in neutron star merger ejecta, excuse me. So basically how much thorium and uranium can be produced by a neutron star merger event and how the nuclear uncertainties can affect that production. So in a neutron star merger, oh, sorry, did you have a question? No. Okay. So in a neutron star merger event, there could be primarily two ways that the material is ejected. So when those neutron stars in a binary system are coalescing, they can tidally deform one another, and those tidal tails can rip off of the neutron stars and be thrown into the ISM. And those tidal tails can be extremely neutron rich. Then on slightly longer timescales, when that binary is ringing down and is coalescing into a final remnant, there can be an accretion disk around that remnant. And there can be some outflows, some wind outflows from that disk, which can also be somewhat neutron rich and can produce R process elements. So what we did in that previous paper is we studied specifically the actinide production in that tidally ejected component because it can be very neutron rich. And if it's very neutron rich, we would expect a very robust R process. So what we were wondering specifically is if something called the actinide boost in metal poor stars can be produced by that specific environment, by that dynamical ejecta. So this actinide boost, they're metal poor stars that are enhanced in these R process elements, but as the name suggests, they have this extra boost of the actinides. They can have a factor of 2 or 3 times more actinides than just a regular R process enhanced star. So we were wondering if the dynamical ejecta of a neutron star merger can be the source of that actinide boost in metal poor stars. And what we found was that in that previous paper, the dynamical ejecta can be so neutron rich, it's actually too much for even those actinide boost stars. You can produce too many actinides compared to what's observed. And what you need instead is some way of diluting that actinide signature down by a lanthanide-rich component. So in a neutron star merger, this could be accomplished by considering that some of that material could come from the accretion disk wind to dilute that dynamical component. So now this paper, after all that, this paper is attempting to quantify how much wind and dynamical ejecta you need in order to explain not only the actinide boost stars, but also some actinide-poor stars as well. And as the title,
how much dilution you need from the disk material to cover for the dynamical component. Is that correct?
Yeah, exactly. Yes, and the title gives it away. Just if you don't want to listen to the rest of this, basically we found that not only can that type of situation where you have dilution from the accretion disk wind, not only that can create the actinide boost stars, but that could also account for the actinide-poor stars. So a neutron star merger, for example, could produce all levels of observed actinide abundance.
Got it. So that would be, in some sense, how the material is then mixed out into the interstellar medium?
Not necessarily how it's mixed, although that could play a very important role. We have not included that in this study. Just how, if there are some variations allowed in the composition of the ejecta, then those variations can account for these different actinide abundances.
Gotcha.
Yeah.
Okay.
Yeah. So what we did is, if you see in figure 2, figure 1 just shows a bunch of kind of the abundant space of stars we use, but figure 2 shows 3 what we call groups of stars. So those 3 abundance patterns represent 3 different, like I said, groups of stars. And why we chose groups is because there were a couple of recent studies that showed that these R process enhanced stars, some of them are related kinematically in the halo, which would mean that they could have originated in the same stellar system, like some dwarf satellite galaxy of the Milky Way. And the reason they're not spatially related is because it's been accreted by the Milky Way and disrupted. So if they were once part of the same system, then it's reasonable to expect that maybe their elements came from the same site or sites when they were originally in that satellite galaxy. So in this plot, each of these groups of stars would be the signature of a single R process event each. And why I chose these 3 specifically is because if you look at that last element on the right, that's the thorium abundance compared to the scaled solar R process abundance. That top one has a very low thorium abundance. The middle one is about solar, and then the bottom one is an actinide boost star. So these 3 are different pretty much in their actinide abundances. And since we're
roughly 5 or 6 orders of magnitude.
Well, these are scaled as well.
But there is a log axis on the y-axis.
Yeah, so it's about 1 dex. So yeah, a factor of 10.
Okay.
Yeah, I did scale these, but they're scaled actinide to lanthanide ratios is about a factor of 10, which 1 order of magnitude, that's enough for an astronomer.
Okay, but is the y-axis a log or a linear?
It is a log, yes,
Right.
but that is scaled.
If I look at J095, right, the thorium is down around -4, and if I look at reticulum 2, Ret2, that's of order 1. So that would be.
Well, I've added like 4 to reticulum 2.
Yeah,
okay. Each of those are scaled. No, sorry.
Okay. It has an arbitrary offset of 4.
Yeah, sorry, an arbitrary offset. I should have said that. Yes, exactly.
Okay, I'm with you now. I'm good. Good. Okay.
And then there is an additional scaling of the solar R process pattern in those gray lines.
Yes. Okay.
Yeah, so I understand the confusion. There's multiple scalings in one plot.
And so we're looking at the pattern here, right? The pattern, independent of the offset, it's the pattern of the R process stuff. So yeah. Very good.
Yes. Yeah. And I do all of this work in ratio space anyway, because I don't know how much ejecta came out of one event. I don't know how much mass it was diluted into. So the best I can do for now in this paper was to work with ratios. So I, to some extent, don't matter what the overall, don't care what the overall scaling is. I'm mostly just looking at the ratio of, for example, thorium to a lanthanide element like dysprosium.
Yeah, dysprosium. Excellent. Okay.
Yeah. Okay, so in figure, oh yeah. Right, okay, so what we're gonna do is I'm gonna use these three groups, say that each group, each abundance pattern represents one R process event that happened in some maybe historical dwarf galaxy. And then I want to translate these abundance differences into differences in the characteristics of the R process ejecta that synthesize those elements. Specifically, I want to reconstruct the ejecta as a function of something called initial neutron richness, or YE. That's Y little e, it's the electron fraction.
Neutron-proton ratio in some sense.
Yeah, pretty much. It's a number of baryons that are protons. So a lower YE means more neutron rich, and a higher YE means more proton rich. And this YE pretty much determines the initial composition of the ejecta. If you have a lower YE, it's more neutron rich. You typically expect that your R process pattern will be more robust because you have more neutrons. Yeah, so that's...
0 is pure neutrons.
Yes, 0 is pure neutrons, exactly. And then 1 is pure protons. Yep. In which case you don't have an R process at all. Yeah, and why we choose YE is because it's just unconstrained, and it sensitively affects the composition of the ejecta. So there are other parameters like the entropy or the dynamical timescale, how fast this ejecta is expanding. But the YE very sensitively affects things like the thorium abundance. So what we did is, first I ran about 100 nucleosynthesis R process calculations using a reaction network code called PRISM. It was developed by Matt Mumpower and Trevor Sprouse, so hats off to them. So we ran 100 of these, changing that initial YE value. So pretty much just changing the initial composition of the ejecta, making it more and more neutron rich. And what we see in this figure 3, the one on the left, is the final zirconium, dysprosium, and thorium abundances as we increase that initial neutron richness. And why I chose those 3 elements is because zirconium, it's near-ish, it's kind of just past something called the first R process peak. So it's representative of production by a limited R process. So it's still an R process element, it's just not, it's not as heavy as the actinides. Yeah. And then I chose dysprosium because it's a lanthanide, so it's that second to last row on the periodic table that's always taken out.
Yes.
Yeah, and then thorium, it's one of 2 observable actinides. It's the one that is easier to observe, but still very difficult. I think now we have thorium abundances for about 30 stars, and we only have uranium abundances for 6. So it's still a small number, but thorium is at least easier. So that's why I chose those 3 elements. They just represent 3 different parts of the R process abundance pattern. And as we increase neutron richness, we can see that the zirconium starts to drop off. The final zirconium abundance starts to drop off. And it makes sense. It's just equivalent to your abundance pattern moving over. So you're getting out of the limited R process region. And if we increase our neutron richness, so decrease the YE, we can finally synthesize our lanthanides, then at even higher neutron richnesses, we finally synthesize our actinides. And then at very low values of YE, so YE less than about 0.18 in this plot, we can see these waves. Yes. Yeah, so those are because of fission cycling that happens. Okay. Yeah. And the previous paper, our actinide production in the neutron-rich ejecta of a neutron star merger. In that paper, we talk about this fission cycling in detail, but it essentially is when you have your R process material, it goes all the way up to the actinides, and then it is so neutron rich still that those neutrons can induce fission on the actinides. Those fission products go around barium, plus or minus depending on your fission fragment distribution. But then if you have more neutrons, they can participate in the R process as well, and they will increase the dysprosium abundance. And then they go up to the actinides, and then they fission again. So that's what those waves are. I thought it was just a really cool effect that we can see in the final abundances, how those fission cycles are going through the abundance pattern.
And that's why they're roughly anti-core. I mean, it's not perfect, but when dysprosium is high, thorium is low.
Exactly. Yeah, exactly. Yeah, because you're really taking that material out of the actinides and putting it into the fission fragment distribution, which could capture just with some more neutrons up to dysprosium. Yeah, exactly. Cool. So anyway, that was an aside. If anyone was wondering what these waves are about. Okay, so yeah, well, good. So now what I have is about 100 different YEs, and then for each starting YE, a final abundance pattern associated with each of those.
Okay.
And now what I do is I built a Monte Carlo method that randomly samples those YEs. It just grabs a handful out of a bucket. It combines the final abundance patterns associated with that handful of YEs. And if the combined abundances, particularly the zirconium, dysprosium, and thorium, if scaled, if they agree with the abundances in figure 2, then I keep that set of YEs and I just put it off to the side for now. And I reach in the bucket and just do it again. I just keep resampling. And after that resampling, I do that hundreds of thousands, millions of times. I do it until the distribution of YEs that I have set aside isn't changing much.
Okay.
Yeah, if it's converged, exactly. Yeah. So that's what's shown in figure 4. So the figure on the right side of this paper, of this page. So each of those histograms are the successful YEs that, when combined, match the abundances of reticulum 2, this group F, and then this fairy actinide boost star J0954.
Okay.
Yeah. And if we look at, so reticulum 2, it's an actinide-poor case, and that's the darkest blue histogram. So if you compare that to the lightest blue histogram, which is an actinide boost, remember the difference between those actinides scaled is about a factor of 10. But I don't think that those distributions look entirely different. Where they are different is in that very low YE tail, so below about 0.2. And that's because, as you just look at figure 3, that's because that's where this fission cycling occurs. And yeah, if these groups are different by their actinide abundance, then our reconstructed distribution of YE is going to be different where the actinides are produced, which is at low YE.
Cool.
Yeah.
When you do the random sampling, is that a uniform sampling?
Yes.
Okay. Okay.
Yes, it is. Yeah, but it does look peaked in the middle. Maybe that's what you're getting at. Yeah, and that's because of that particular YE. That is where an optimal thorium to dysprosium ratio is found. Mm-hmm. Because at that YE, you're not overproducing the thorium so much. You're producing it at a nice low level. Right. So that's why it tends to favor something at around 0.25.
Yes. I'm with you.
Yeah. Okay, so then, yeah, I don't think these distributions look very different. So next what we did is we asked, well, we tried to quantify this difference. Yes, so the next will be figure 6. Figure 5 just shows those combined abundances, and they match the pattern. They match the pattern pretty well considering we're only using 3 elements. So I was pretty happy to see that. Yeah.
Okay.
And the top is for the actinide-poor, the middle is for an actinide normal, and then the bottom is for an actinide boost. But the figure I wanted to focus on is figure 6 here. And how to read this plot is on the x-axis, increasing thorium abundance, increasing actinide abundance. And then on the y-axis, how much of that very low YE, fission cycling, actinide-rich, possibly dynamical ejecta do you need in order to match that thorium abundance?
Okay, and what's the 0.18 on the y-axis?
Yeah, that's the fission cycling. So if we scroll back up to figure, what would that be? Figure 4.
Okay.
And figure 3, I guess. That 0.18. Yeah, it's where that we see kind of that dip, because everything below that will be fission cycling.
I'm with you. Okay.
Yeah, so I chose 0.18 because after about 0.18, that's when it fission cycles. So it's just asking what percentage of the total ejecta needs to be fission cycling or could be fission cycling in order to match each of those abundances.
With you. Yep.
And what struck me about this plot was a couple of things. And what we did here, sorry, let me just take a step back, is I just systematically changed the required thorium to dysprosium ratio, then ran my Monte Carlo method and just calculated how much of the mass is at low YE, what percentage of it is at low YE.
Yes.
And each of those dots are just for individual stars. Okay, so yeah, what struck me about this plot was just how smooth it is.
Let me go back. The circles are stars. Those are observations.
No, they're not. Sorry, my mistake. They're not really observations. So what is an observation is the x-axis value. So I chose the observed thorium to dysprosium and zirconium ratio, technically. And then I put those abundances in my Monte Carlo method, and then asked how much of, I calculated a distribution as in figure 4, and then took how much of that mass is at low YE.
Okay. Okay. Thank you.
Yeah, sorry. I am famous for my complicated plots. So what struck me about this plot was that there's a smooth transition from very actinide-poor, which would be that last point all the way on the left, all the way up to actinide boost. I don't see any great jump.
No, yeah.
Yeah, so this tells me, well, okay, maybe it could be the same site. And then if we look at the very actinide-poor cases, that means it says that about 10% of your total mass needs to be or could be fission cycling. But if we look at the actinide boost cases, it's 30%, maybe up to 40%. And okay, as an astronomer, the difference between 10 and 30, it's a factor of 3. That's not, as an astronomer, that's not a lot. It's a factor of 3 to explain a factor of 10 in actinide abundance.
Right.
And between a factor of 10 and between 10% and 30%, that's still not a dominant component. So what this plot is basically saying is that, well, if you have the same type of R process event, and in one case you eject 10% as, for example, a dynamical ejecta that is very fission cycling, then you can create an actinide-poor star out of that ejecta. But if you allow just a little bit more of that dynamical component, so up to about 30%, then you can create an actinide boost. And that's, again, to me, that's not a huge variation. 10% to 30%. It's, again, it's still non-dominant. It means we still need a wind component in a neutron star merger in order to dilute that actinide.
You don't need something particularly special.
Right.
It's small variations will give it to you.
Exactly. Yeah. And before this, there was a lot of speculation as, okay, we thought that actinide boost stars were made in a different site, that they were a distinct R process pattern made by something else. You know, maybe it was thought that maybe actinide boost stars were made from a neutron star merger, and maybe the regular R process enhanced stars came from some exotic supernova. I don't know. Right. But it was thought that they had two different progenitors.
Mm-hmm. Mm-hmm. Oh, yeah. People talked about this for years.
Yeah. Yeah, and what we're finding is, you don't really need a different progenitor. You just need one progenitor to behave a little bit differently sometimes.
Right. So let me just put a little perspective on that. Right. So people, talk about for decades how you needed different populations of supernovae in order to get these different components. And so what is disruptive, if you like, about this work is that shows that's not the case necessarily. You can get away with one population, one scenario, neutron star mergers in this case.
Yeah, for example. Yeah, exactly.
This is what is disruptive, although your plot is smooth, so it's disruptive because it's smooth.
I didn't know I was a controversial researcher.
yeah, no, okay. Very cool.
Yeah. We also, just to test the robustness of what we did, these are just some supporting plots, but on the next page,
okay.
We also tested some astrophysical variations. So, sorry if you keep going. So yeah, that one. Yeah.
Yep.
So what we did is, okay, when we ran all of our nucleosynthesis simulations, we chose essentially the same, what we call an astrophysical trajectory. So the same, the way the ejecta behaves in time, both its temperature and its density is the same. And what we changed was just the initial composition. But a hydrodynamicist would tell you, well, the way that the ejecta behaves sets your initial composition, so those things are related. And it's true. So what we did is we also changed the entropy of the ejecta, where we used a higher entropy trajectory for the higher YE parts, and then we kept a lower entropy for the low YE part, and then we just sampled between the two of those. And we called it an entropy mix and an ejecta mix. And this plot is just showing, well, overall it kind of looks the same. The details, the shape of it may be different, but in general you still end up with this low mass, low YE tail.
So
we also
robust.
Yeah, and it's robust under some nuclear physics variations too. So I am at heart a nuclear physicist, and that's what our research group, what Rebecca Sermon's research group specializes in. So if you go to the next page, what we did is we reran all of our nuclear input. So we changed all of our nuclear input to be consistent with two different nuclear mass models. So in all of these, I was using something called the FRDM 2012 mass model. But I changed all of the nuclear input to be consistent with Duflo-Zucker masses. And then I changed all of it to be consistent with this Hartree-Fock-Guliabov mass model.
HFB, yep.
Yeah, HFB, yep. And then I did everything over again. So I reran all of those trajectories, all 100 of them, well, twice for each mass model. Reran the Monte Carlo method. And these are the mass distributions that I get. It's pretty much the same. The plot on the right, figure 11, is the same as I think it's figure 6 before. And I just have those variations in them. So
a little more scatter though, due to the nuclear physics as opposed to the astrophysics, if you like.
Yes. And that's because those two mass models produce less thorium in general. So you can allow more of your low YE component to make up for that loss in thorium. But still, it's a variation of 5 to 10%, 10% at the most.
Right. Okay. Awesome.
Yeah.
And which leads to the conclusion, which happens to sit right in the title of the paper, is that you do. So let me ask you, given this work and relatively recent, 2019, where do we go from here? Given what you published, what's the next steps?
Oh my gosh, there's so many other steps. Well, one thing is with these dynamical groups. So when at the time this was published, we were basing our dynamical groups off of Ian Roeder's 2018 paper, and in his paper they identified, I want to say 8 groups, maybe it was closer to 10. So they identified 8 separate groups in the Milky Way halo that were related kinematically. And that was great, and that inspired a lot of other works, because I think it was Zhen Yuan just published this year a similar work where they have identified even more of these groups.
Okay.
And that just gives us more data to work with. I can now run this method on all of those groups. And as an astronomer, we can target those groups and get better thorium abundances. I don't even know if all of them have thorium abundances, but we can measure them.
Follow it up,
And then run this analysis. And on the theory side, one can ask, what is the source of these variations? So I said, if you allow your astrophysical site to have these types of variations, what causes those variations?
Right. Right. Why would you get a different entropy, or why would you get a different neutron to proton ratio?
Yeah. Why would you have more or less YE? Yeah, exactly. And then personally, just to advertise what's coming next, is I accepted a position at Rochester Institute of Technology. So that's where I will be doing my postdoc.
Very cool. Very good. When do you start that position? I
start in August.
Okay.
Assuming I can move.
Right, in the current epoch. Hopefully we're past it, or the bulk of it anyway by then. Well, I'm very happy for you. That's wonderful. So for people who are interested and would like to follow up, Erika just sort of gave where her coordinates are. You can feel free to contact her by email. Although we won't be broadcasting email here on YouTube. But in the video down below, I will put links to the paper. I will put links to Erika's website, and feel free to reach out to her. And I think that'll do. And Erika, I want to thank you so much for your time this morning and chatting with me about your very cool paper.
Well, it's a pleasure. Thank you for having me.
All righty. Bye-bye, everybody.